So thank you very much for the time to present to you all today. I'm going to talk about some work on foundation models, which I think was already a topic in Ben's previous discussion. I'll be focusing mostly on models that don't involve text, so models for other signal modalities that are relevant to mHealth research. And I want to start by giving you a canonical example. So this is a model that was developed in the vision community called DynoV2. And the key property of this model is that it was trained on massive data, and I'll give you an example of that in a second. And that means that we believe that this model kind of covers the domain of the data, meaning that it can represent, in this case, many, many different things that are present in images. And the second thing is that this is a single representation which is capable of solving multiple tasks. So just to put a little bit more structure on that, so this is a model with 1 billion parameters, which is not the largest model by a long shot that you can find today, but still a very large model. It was trained on a very large amount of images, as you can see here. And the cost of training was, extremely high, so something that is out of reach for most academic research groups and many companies as well. And the good thing about it is that it's freely available to the community. So Meta trained this model and then essentially gave it away, allowing others to take advantage of it. Now, this model can be used to solve multiple tasks. On the right, you see 2 examples. So there's at the top image, there's what's called depth estimation, which is estimating how far away the pixels in the scene are from the camera. So the table is close to the camera, so it's bright, and the wall behind the couch is far from the camera, so it's dark. And this is done by analyzing this single image, which is quite a remarkable accomplishment. Now, this same model, with no fine-tuning, no training on additional data, can also solve the second task, which is semantic segmentation, which is given the image, it labels the pixels with the object that they belong to. So the blue pixels correspond to the couch, the yellow pixels correspond to the pillow, and so forth. So it's this ability to solve 2 quite different tasks and several others besides, using the same representation, the same encoding of the image. That is what makes this the foundation model in some sense and gives it its power. So this is kind of the context that, in my view, is extremely important for mobile health and health AI research in general, that we have these extremely powerful models that are available today for domains of data that are truly widespread, like text and images. And the question then is, how can we use these models to advance our agenda in health, where the data is often not large scale and often available only at high cost? Right, and so this is kind of 2 key questions here that we want to address. So one is, how can we take existing foundation models and repurpose them for health-related tasks? And there's basically 2 approaches to this. And Ben talked about the first approach in his presentation, which is this idea of prompt engineering, where you essentially don't touch the representation and don't interact with it at all, and simply provide natural language instruction to essentially tell the model what you want it to do. And this can work well in circumstances, particularly where text is the desired output. But in my experience, it's often not a super great approach, because natural language is often a relatively poor API for describing what you want in terms of modeling. And there's also some issues of non-robustness because these models are not well characterized right now. The alternative, which I'll show you in a second as another way to go, is to train what's called task-specific decoders for these models. And this is also challenging. It requires some creativity. It requires machine learning expertise. The only thing that makes it attractive is that in the end, you get a well-defined module, which is easier to understand, I would argue. It can be repurposed in some cases. Okay, so these are 2 strategies for taking advantage of existing models and reusing them. And the other option is to create our own foundation models, to create a foundation model for a new modality, for example, time series data, as Ben was talking about in one of his questions. And there we have these standard questions for all models of this kind, which is, how do we get enough data, and how do we accomplish what's called self-supervision? And I'll show you an example of this as well in a few minutes. I want to give you an example from our research that we're conducting here at the University of Illinois around repurposing these vision foundation models for understanding children's behavior. So this is not exactly an mHealth application, although it might become one if wearable cameras become commonplace in the future. But I just want to use this to illustrate this idea of repurposing an existing foundation model. So the way you define the task is shown in this slide. So there's an individual, in this case the boy, and you identify his head with a bounding box, and you ask the model, where is that individual looking in the image? What is the target of their gaze? And then the output of the model should be a heat map that indicates locations where the gaze of that child might be directed. In this case, the area where he is decorating the cake is highlighted with this heat map. And then you have to address the fact that sometimes the gaze target is not visible because it lies outside the image. And so the model has to produce the heat map and I don't know response in the case where it can't see the target. And the training data for this model is simply asking people, where is the child looking? And they click little dots on the screen there, and those dots become the ground truth for training a model. So this is actually a well-studied problem in computer vision. My group has worked on this over the years, along with many others. And in prior approaches, people built these giant models with lots of complex training data sets, trained end-to-end, meaning the model was essentially trained from scratch. And we asked the question a few years ago, could we use foundation models to solve this problem? And this is not a trivial question because the models I showed you, like Dino V2, they were not designed with children's behavior in mind, with social behavior in mind, with any kind of human characteristic really in mind. They were designed for a very different set of tasks, more like autonomous driving kind of tasks, for example. And so it was an open question until recently whether or not these models could actually be applied effectively. And so it turns out they can. And this is a paper my student Fiona Ryan's work. This is a paper we're going to be presenting at a computer vision conference called CVPR this summer, next month. And what this architecture shows is the ability to take this Dino V2 model, which is the big block on the left, and we freeze it. We don't touch it at all. We just take the representation that it produces using the model weights that were provided by Meta that we downloaded. And then we have built this architecture to the right, this series of layers that take that output of this Dino V2 and effectively decode it into the heat map you see on the far right. So this decoder converts the representation that we get for free from Meta, and then organizes it in such a way that it can be used to solve our task. Now we need some training data to train this decoder, to train these blocks that you see on the right. But luckily, the training data we need is much, much smaller than what you would need to build the representation in the first place. So the exciting point about this is we can use much, much less data than you might expect under normal circumstances to get a high quality, high performing model, because we can leverage the power, the representational power of these existing foundation models. And so this just shows that our model is currently the state of the art for these gaze analysis tasks in comparison to many other models that were published in the past. And the main thing I would highlight is the first column, which is that our total parameters, about 3 million, are an order of magnitude less than all the previous approaches. And that reduction in parameters is directly translatable to the need for less data. And this is, again, because we can leverage the pre-trained model that has 1 billion parameters and already encodes the visual world quite effectively. Here's how the model performs in practice on the testing set. That was a mistake right there. So it's not yet operating at human level accuracy, but that's our goal in pushing this forward. But I would argue that it is working, pretty well, and I think we can make it work quite a bit better as we continue to refine the approach. And then this is an example that is now relevant to autism. So this is a child engaged in the joint attention task, where she's interacting with an examiner around a toy, and she uses her gaze and other aspects of her kind of social skills here to communicate. So it's nonverbal communication based on gaze, gesture, facial expression, etc. And our goal is to automatically analyze these social behaviors to get a better insight into the kind of the characteristics of autism, the etiology, and the treatment that works for this condition. All right, so this was an example, rather quickly, of taking an existing model and repurposing it. And this approach of training a decoder requires some engineering and some machine learning expertise. So it's not necessarily for everyone, but the advantage is that it can produce these really well characterized models that are then, can be made widely available actually for specific tasks. And this is also exciting because it means that we can rethink how we approach validation of these models. So in the past, getting enough data to train a model was so difficult, it was very hard to really imagine doing comprehensive validation. But now that we need much less data to do both training and validation, we can really become more ambitious. And we're thinking now about how could we actually collect a sufficiently large data set that we could validate these models on a very broad representative population. So this would be pulling together videos of children from all over the world, and then testing whether or not these models are effective on this broad population of data across many different tasks and settings. And this is an effort that we're getting started with right now to pull together such a universal kind of validation data set. All right, so that was a quick tour through repurposing existing foundation models with computer vision and autism as a health context. And I want to change gears now and talk about a more traditional and extremely important kind of mobile health context. And this may be a review for you already based on the presentations you've seen, but I just want to emphasize the issue that currently in our healthcare system, the key drivers of outcome and cost are these conditions known as chronic health conditions, meaning there's no medical cure, there's no drug that directly solves the problem. In many cases, there is no cure for these conditions, but they can be managed and they can be prevented. And the burden of these conditions is growing over time and with significant impact on mortality and cost. And the key property of these conditions, a key property, is that they often are linked to mutable risk factors like smoking, obesity, poor diet, etc. And so this linkage has spawned this vast literature and interest around using mobile health technology to bring about behavior change and enable people essentially to change their behavior more effectively. A particular context for this that's relevant to my lab is this growing rural-urban divide in health outcomes, which you may be familiar with. This is a graphic from an interesting article in the Washington Post a few years ago. And what it shows on the y-axis is simply the progression of time from top to bottom. And on the x-axis is death as a function of population. And what you can see is that in the 80s, rural areas shown in green were more or less in the same range in terms of mortality as urban, as major cities and their suburbs. As time went on, the health outcomes for the urban communities improved essentially. The rate of death shifted to the left and became reduced, and rural populations did not see that same gain. And then around the late 90s, we began to see this strong separation where essentially outcomes for rural areas are much more challenging, much more negative than for urban populations. And so this rural-urban gap in health outcomes has now become a significant public health issue in the US. And there are a variety of reasons for this separation. And so there's no magic bullet for this complex problem. But finding ways to use mobile health technology to reach individuals and communities that often have reduced access to healthcare and at the same time, worse outcomes is an important agenda for the center that I'm running at UIUC. Okay, so then the question is, what can we do about it? And so I just want to take you through a little schematic, and this again may be familiar to you, but this is a little schematic around how you might use behavioral intervention to improve outcomes. And so in this example, there's an individual who's trying to quit smoking. They've begun a quit attempt, and they enter a period in their day of what we call increased vulnerability. For example, they might have these bouts of high stress due to some work-life interaction, some issue with their partner, some issue with their commute, etc. And because of this stress, their vulnerability is increased, and that increased vulnerability in the moment could lead in several hours later to the adverse outcome that we're trying to prevent, which is a lapse back to smoking. And so the idea then is to use technology to intervene in such a way as to improve or reduce the proximal outcome as a way of then affecting and improving the distal outcome. So you'd like to reduce the person's stress so you can help them to maintain their abstinence. And the way that we think about doing this is by having some way to analyze mobile sensor data and extract some risk marker. For example, identifying the stressor that somebody is experiencing, ideally identifying it before they actually experience the stress. So you can imagine predicting that someone is about to begin a commute, and then knowing that often their commute is a source of high stress for them. And having that window in time into the future where the risk may occur, that gives you an opportunity to intervene and to possibly give the person tools or suggestions or other strategies they can use to manage that stress that's coming, and then hopefully maintain their abstinence, improve the distal outcome. And so this is the idea of an adaptive intervention that is based on the ability to sense these risk markers from the mobile health data that we get from the wearable device. And then having succeeded in doing that, we can then reduce the stress to a manageable level and then preserve abstinence by removing the distal outcome that we want to avoid. So this is the idea of what's called a just-in-time just in time because we deliver it when it's needed, adaptive intervention, adaptive because it's contextualized based on the person's status and where they are. So there's a huge literature about this, and I'm not going to go into the details of how you might design and deliver a JIT-I. Hopefully you've gotten that information already in other presentations. What I want to focus on is how we could take the same kind of foundation model approach and bring it to bear on these exciting possible applications of machine learning in mobile health. And so the idea then is to find a way to generate these risk indices based on the ability to extract and estimate these risk factors or risk markers. And having done that, you can imagine something as simple as thresholding to decide when to intervene. So this risk marker that tells us essentially what the status is can be a very useful direct way to do intervention. And then just to mention another important aspect of this, that effectively, we have this ability to analyze data and establish correlative relationships, some correlation between, for example, stress and smoking lapse. And we can do this through an observational study, identify these correlations, generate hypotheses about, what might be effective. For example, we could hypothesize that a mindfulness intervention might be effective in maintaining abstinence. And then we have to establish that this is actually a functional relationship, a causal relationship that matters in terms of outcomes, and avoid possible confounds. And for that, we have other tools like a randomized trial we can use to study these causal effects more directly. So the ability to sort of mine relationships between cause and effect from observational data and then generate hypotheses can then be used through a series of additional steps and additional tools to develop intervention strategies and approaches. So the linchpin of this is the ability to leverage mobile health data to infer these states of risk. And there's sort of three areas in general where this data can be very useful. So I already mentioned this idea of generating these kind of hypotheses for causal effects from observational data. That's possible because we have these risk markers that give us the ability to identify specific causes of risk like stress in the moment. And then a last thing that these models can provide us with is the ability to detect the outcomes in a low burden way. So for example, if we can detect when an individual is taking puffs from a cigarette, then that provides an ability to automatically determine whether or not the adverse outcome took place without having to ask the participant to self-report on their smoking behavior, for example. And so then the question comes, how can we advance mHealth and AI in such a way as to meet these needs? And there's a variety of challenges that have to be addressed, and I'll just quickly take you through a couple of them here. So the first challenge is that we're always going to be limited by the wearable sensors that are available. And not just the wearable sensors that are available, but in many cases, the ones that people are willing to wear. And so these are actually quite strong constraints because people often are not willing to buy and wear devices simply to improve their health, particularly in a prevention context where people don't have a diagnosis already. They don't have necessarily the motivation to sort of consume wearable health technology. Okay, and this is an area that's quite complex, but there's a lot of activity, a lot of ideas being generated right now. And one of the things that's extremely important, and we're seeing quite a bit of progress, is the creation of novel sensors essentially that can yield new markers. So there's this exciting development in the sensor front that can give us new risk markers for conditions that go beyond what you can get from simply a wearable wrist-worn device, for example, or a smartphone. Second challenge is that the data that you get from these sensors is, generally speaking, quite complex and often has substantial missingness due to various issues in the field environment that I'll talk about more in a second. And so there's a question of how to do effective imputation in order to be able to fill in wherever data is missing. And I'll show you a finding for that we had a few years ago in my lab. And the last challenge is, as I was alluding to already, is the lack of these effective foundation models. So for these biosignals like accelerometry or PPG, we don't have the same level of technology that exists for text and images. And there's a question of how to approach that and how to solve that gap, close that gap. All right, so I'll talk about each of these three in a bit more detail. I just want to showcase here some work by my colleague. This is now a couple of years old at Georgia Tech when I was on the faculty there. This is my colleague Omer Anand's work, and this is a very interesting chest-worn patch that uses a sensing approach called seismocardiography to directly measure the heart function. So most of our ability to assess heart function is very indirect. We look at the pulse transit time, for example, and with calibration, we try to measure the blood pressure. But this is a very hard problem where the solutions that we have today are not very robust. Or we might look at just the electrical activity of the heart, the ECG, in a wearable setting, but that doesn't actually tell us about function. It just tells us about rhythm. And so this is the device that can measure in a much more direct way the heart function and provides new windows into, for example, looking at the risk of decompensation in heart failure, which is a classical kind of chronic health problem that's received tremendous attention. So really the point is that the space of opportunity here for novel devices to be invented and then utilized in various parts of the body is really high right now, and the technology is advancing rapidly. And I think there's going to be this tremendous downstream set of possibilities for the exploitation of these sensors as they become mature and become, increasingly available. But all these sensors have the problem that they are plagued by missing data. And this little graph on the right just shows all the different reasons why data might be missing from some mobile sensor. Different issues related to the device itself, its function, its use by the participants, and then just properties of the environment. And all these things are quite complex and interact in such a way that samples become missing. And the standard approach to missing this is to just throw away, the chunks of the signal where samples are missing, and don't try to measure the biomarkers of interest during those corrupted, periods of time. But the problem is that often markers of interest may aggregate data over a very long temporal window. So something like heart rate might utilize data over several minutes to get accuracy in terms of estimating the heart rate. And if you throw away windows of data where there's missing samples, you can throw away these large portions of the signal and end up with very little data that you can actually use directly for your model. And so there's a real need to address missingness through imputation rather than simply discarding the data. And the challenge is to do this accurately. And so we began approach to this problem a few years ago, trying to exploit the fact that many of these interesting mobile health signals have this sort of pulsative nature. They're kind of quasi-periodic signals that repeat, not exactly, but with some regularity in their morphology. And this is because they all come in directly or indirectly from the function of the heart and its interaction with the lungs and the body. And that produces a rhythmic pattern that characterizes many of the signals you see on this slide. And so the question we asked long ago was, how could we exploit that structure to solve a problem like imputation? And so we did some work on both collecting and then training an imputation model on a large cohort, a large collection of mHealth signals. And the approach here is actually very straightforward. If you can find a set of data where there's relatively little missingness, so a representative data set where the missingness is relatively low, then you can essentially simulate missingness by simply blocking out, a set of samples selected at random with a window of a certain size. In this case, the gray window you see on the right is blocking out a variety of signals, removing those samples. And then you can train a deep learning-based model whose job is to impute the missing samples. And that's a well-defined problem because you know which samples you removed, so you know what you did to the signal to cause it to become have missingness, and then you can train the model to reproduce those samples that you removed yourself. Okay, so once you do this on large scale, then you can apply this model to signals where the samples are gone for naturalistic reasons in the field environment. And so one of the key ideas here was to capture the patterns of missingness that actually arise in the real life environment. And so we were able to get access to a very large data set in a smoking cessation study that we were involved in. And you can see here on the right some of the missingness patterns in this data set. And we were able to take these missingness patterns, essentially the intervals where data was gone under various conditions, and then apply these missingness patterns to a data set where we have access to most of the samples. So this allows us to play this game of removing the samples ourselves and then asking the model to reproduce them or to impute them. But doing this in a way that captures the real life patterns of missingness. So this is actually then applicable directly to a real world scenario. I'm not going to go into all the details here in gory detail, but just to show you some findings. So this is a model that we created and published a few years ago at NeurIPS and it's at the top is called BDC transformer. And you can see in this little schematic that this area that's grayed out is where samples were ablated, so samples were artificially removed. And then the blue peaks that you see in this graph are the imputed values of the signal from our model. And you can see qualitatively here that our model is doing a better job of capturing the morphology of the ECG signal in this case than many other competing approaches. And this is possible because this model has a very long context window using kind of attention mechanism that's available through transformers. And it's able to look across this waveform and find relevant places where the signal that it's looking for could be identified and then used to recreate the signal in the areas where it's missing. And this is the ability to efficiently exploit this large context window is a property of this model that's not available for other models that we are competing against here. And then there's some, in the graph on the bottom, there's some quantitative results showing that our approach to imputation leads to improved accuracy in downstream classification tasks for using the signal to classify some property of the waveform. And so this shows that the imputation is more effective in capturing the meaningful properties of the signal because it leads to improved accuracy across a variety of downstream tasks. These are all examples for ECG. We have similar findings for PPG. And this model is freely available. So if you happen to be in a situation where you are working with ECG or PPG data and you'd like to do imputation with a high quality model, you can simply grab our code and our model weights and run it directly on your data. All right, so we've talked about the excitement around novel sensors that are coming, and we'll need, of course, to use AI methods to interpret and analyze the values produced by these novel sensors. And we talked about the fact that all of these mobile sensors, whether they're novel or whether they're watches and smartphones, have this problem of missingness and how it could be addressed. And now I want to turn to the last question, which is how could we actually, given a sufficiently large data set, how can we train our own representation? How can we train our own foundation model with sufficient data? And the key here is that we need to train this model in such a way that we don't require tremendous amounts of labels. So there's two issues in mHealth. There's getting enough data, enough samples of relevant signals like accelerometry, for example. And then there's the question of getting enough labels. And the label question is the hardest because labels typically require you to ask people or ask experts to identify when something important happened and then label the event, the important event. And this kind of labeling effort is high burden for participants and expensive for experts. And so labels are always going to be in scarce supply. But as data becomes increasingly available, we can leverage an approach that has worked really well in the computer vision and NLP areas, which is what's called self-supervision. And I'm showing one example of this here for an image analysis task. And this is an approach called SimClear that was a groundbreaking paper in 2020 that really demonstrated an effective approach to large-scale self-supervised learning in images. And the key idea behind this approach, which you can see in the schematic on the right, is that there are important invariances that exist for images. And because of these invariances, you can take an input image and you can change it in a variety of ways so that the pixel values are changed in some substantial way, but you don't change the meaning. And so for the dog you see on the left, if you take that image of the dog that's at the bottom, and if you just crop the image randomly, just crop out a portion of the image, then what you're left with is still an image of a dog. The meaning of the image has not changed. It's still a dog, but the pixel patterns now in these cropped images are quite different than they were in the source because the pixels of the dog's head, for example, cover a different part of the image and have different level of details and so on. Likewise, for the image of the chair on the right, you can take that image and just recolor it, perform some color jittering, as they call it, that adjusts the color values randomly. And that change in the color doesn't fundamentally change the meaning of that image. It's still a chair. It's just maybe a green chair instead of a red one, or a black and white chair instead of a color picture of a chair, but it's still a chair. Via this approach, we can take these images, transform them, and obtain pairs. The pairs are images that are the same meaning, but are different because they've been augmented. And then we can train a model that basically has the job of taking the pairs that are similar, like these two pictures of the dog on the left branch, and it tries to map them into an embedding space where those images are close together because they're similar. And then it does the same thing for the chair images that are color jittered. It maps them to an embedding space in such a way that they're close together. And then because dogs and chairs are not the same type of object, and it knows that, then the same approach can also map those dogs and chairs far apart in the embedding space. So you create essentially a loss function here that will organize the representation space so that images that have similar meaning are grouped together. Images with reduced meaning or less similar meaning are farther apart. And you can do this without knowing that it's actually a dog. All you need to know is that there's an object in the image that's salient or significant, and then you just apply the transformation. So this approach in practice requires no actual labels, just a data set of objects that you can analyze. This was very effective, okay, and produced quite powerful vision representations. But the challenge is, how can you do this for time series data? What are the natural invariances in time series data? And it turns out that there's very few of them. And so this requires us to invent a different approach to contrastive learning that can produce a different mechanism for identifying these pairs of positive and negative examples. And so I'm just going to report briefly on a recent paper that we published with Apple Health at a conference called iClear, a machine learning conference that took place earlier this month in Singapore. And this is a model for motion data, which means accelerometry data. And this is, I would argue, this is the first kind of real significant accelerometry foundation model that's been produced up to date. And so the key idea behind this work is that we have to, again, find a way to generate these positive pairs. And we're going to do this for these signals like accelerometry that have this repetitive or quasi-periodic structure. And so what this illustrates in this figure is a day-long time series recording of accelerometry, your watch accelerometer over an entire day. And in that day, because humans have repetitive behaviors, there's many things you're going to do over and over again. You're going to sit down, you're going to get up, you're going to walk. And during those intervals, when you're performing the same activity, there are going to be subsequences of this data that are very similar. So as you walk, for example, the way your arm sways is going to be the same when you do it at 1 o'clock and the same when you do it at 4 o'clock. And so that arm swing is a little snippet or a chunk of accelerometry samples that's going to have similar morphology because the pattern of motion is very similar. And so the idea here, without going into the details too much, is to use the same reconstruction approach I showed you earlier and identify ways to reconstruct one portion of the signal from other portions of the signal, where the reconstruction loss is simply asking, can we find similar matches, similar structures in one part of the signal that can allow us to reproduce the structure in another part of the signal? So it's essentially matching these signals via reconstruction. And the attractive part of this is that you can train a model in the purely self-supervised way to perform reconstruction. And then you can look at the quality of the reconstruction as a marker for similarity. So if I can reconstruct one little chunk of a signal very accurately using another little chunk of the signal, then those two chunks are probably very similar in their structure. And we hypothesize in that case, similar in meaning. Okay, so this is an indirect way to get access to semantic similarity, but it has the advantage that it can be used without any labels at all, just on long recordings of wearable sensor data. So the hypothesis then is that this approach I described, you could think of this as kind of a motif-based approach, where each of these little snippets is like a motif, a kind of a unique pattern, if you will, in the time series data, and we have ways to then match these motifs over time. And the hypothesis is that this will produce an effective representation. And so we're able to get access in this case to a large data set that Apple maintains, which is a closed data set. You can see the statistics here, more than 1 billion accelerometry segments, so a massive amount of wearable data. And there are corresponding large-scale data sets that are open, like the UK Biobank, that could also be used for this kind of model development purpose. And I won't go into this architecture in detail, but this just explains what I talked about earlier. This is the ability to essentially identify the matching function, learn the matching function for measuring the distance between these little snippets of signal via this reconstruction-based approach using a standard transformer architecture that's now kind of standard technology in the literature. And then with this ability to do reconstruction and to use reconstruction to perform matching, we designed a new loss function that allows the model to do contrastive learning, essentially putting similar and different snippets of signal together and apart in the representation space. And this approach has produced what we think is the most effective representation space to date for accelerometry. And one illustration of this is by looking at these TS&E plots, these two-dimensional visualizations of the representation space itself. In the top left, you can see our model's representation space. The other three figures show competing approaches. And you can see that our approach produces this very kind of finely distributed representation space where different groups of accelerometry signals corresponding to different activities. These are activity recognition tasks in a field setting. They're quite separable. So, for example, we have good separation between two different kinds of bicycle riding, indoor versus outdoor cycling. These would normally be smushed together into the same cluster in previous approaches because the representation space is not as refined. We also find a very small cluster that corresponds to swimming. Swimming is often lumped in with other activities in these other approaches because of the similarity of some of the motion patterns. But this is kind of a qualitative finding that shows that this new foundation model for motion data seems to be producing a very fine-grained representation space that can distinguish between different kinds of activities in terms of the organization, if you will, of the samples in the representation space. Another argument for the performance of this representation, excuse me, is based on the accuracy and the performance. So this is the performance of our approach on activity recognition. We're doing better than previous approaches across a number of metrics, and then also recognizing what workout someone is doing as well. Skip over this plot. We're also doing a task that's called gait metric regression. It's a couple of tasks of predicting gait parameters like stride velocity from accelerometry data. Once again, we have the state-of-the-art performance right now for these two tasks based on the wearable accelerometry. And I'll just wrap things up and take a few questions. So we talked about the ability for mobile health technology to give a means to provide interventions to remove risk. And this is tied to the ability to learn effective models of signals that can produce various risk markers. And we talked about how that could be done by training foundation models from novel signal types like accelerometry data, and also by repurposing existing foundation models in areas like vision and language where powerful models exist already. And the current RelCon model that we introduced last month is the state of the art right now for a motion foundation model. Thank you.
Thanks, Jim. There are a couple of questions that may have bled over from Ben's talk. Would you want to address them?
Yeah, I'll take a few questions, and then I got to jump.
I think they're in the Q&A.
Could you repeat them for me?
Jory asks, just wondering why these models don't have safety built in, more philosophical and ethics driven.
Yeah, this is a big problem right now that many people are addressing. They don't have safety built in because they don't know how to do it, basically. The goal of these models is to generalize to unseen examples. And that generalization itself creates a source of risk because you could generalize in ways that are wrong. And we just don't understand these models well enough right now to really provide effective ways to control their generalization. So this is really an open problem that many people are working on right now and hopefully will be addressed in the coming years. That's my hope.
Tiffany, do you want to read out your question in the chat? Tiffany Glynn.
Don't be shy.
So I think her question was in thinking about using LLMs for behavioral mental health interventions in mHealth. Our biggest fear is that the LLM produced language would be detrimental, adverse. Any other ways to put boundaries or parameters or containment on what the LLM could output?
Yeah, so I think it's really the same question. So, you're probably familiar with the standard ideas of guardrails doing what's called a retrieval augmented generation, where you try to go back to source texts and find specific, snippets of text from the source that you believe are responsive to the question that's been asked. So then rather than generating the model's text itself, you might find text that you believe is authoritative or relevant and use that text as part of your construction of an answer. This is a standard approach. Many people are doing this today, but this does not remove the challenge. This does not eliminate the problem of hallucination and so forth. So really, I would just say this is an open research question. I don't think there's any magic bullet for this. Right now, I think the only thing that really works is either a human in the loop approach, where humans somehow check everything to make sure that it's correct before it goes out, or a kind of post hoc approach. In certain applications, you can go back after the thing is generated and fix it post hoc if that's appropriate for the task at hand. So note-taking applications in medicine use that post hoc approach for the doctor reviews after the notes have been created and make sure there's no problems with it. These are both obviously labor intensive and not ideal. I think I'll stop there, Vivek, so I can jump to my next.
Jim, yeah, terrific. Thank you very much. Appreciate very much.